In the 1580s, the King of Spain had a problem, though it took him some years to notice it. Philip II ruled the largest empire on earth, and running it meant sending orders across thousands of miles of hostile territory, including to his agents and allies inside France, where a savage religious civil war was underway and Spain was backing one side. Those dispatches were enciphered, and the cipher was formidable. Several hundred characters, with multiple symbols for the same letter, nulls to confuse the counting, and code groups for common words and names. By the standards of the age, it was state-of-the-art, and Philip's cryptographers considered it unbreakable. The French were reading it. They were reading it because a lawyer in the royal service named François Viète, who did mathematics in his spare time, had sat down with a pile of intercepted dispatches and taken the thing apart. What Spain believed was armor, Viète treated as a puzzle with a structure, patterns of repetition, frequencies, the shapes that language makes when you squint at it sideways, and he found the structure and read the mail. The story that has come down to yes is that when Philip learned his ciphers had been broken, he found the possibility so far outside the natural order that he complained to the Pope, on the grounds that the French must be employing sorcery. Whether the complaint happened exactly as described, historians argue about. Whether it should have happened is not in doubt. A man had looked at a wall of meaningless symbols and made them speak, which is a decent description of what Viète did to mathematics, and it turned out to matter more than the codebreaking. He was born in 1540 in Poitou, trained as a lawyer, and spent his career in the service of great families and eventually of 2 kings. Mathematics was not his profession, it was his obsession. He worked at it in the margins of a political life, and by contemporary report he could disappear into a problem for 3 days at a stretch, not eating, not sleeping, barely aware that anyone had come into the room. In 1591, he published a short book with a forbidding title, Introduction to the Analytic Art, and inside it he did something that had never been done. He used letters for the numbers you already know. To see why that is a revolution, and not a stylistic quirk, we have to be precise about what came before. Letters for the unknown were nothing new. Al-Khwarizmi had Shay, the thing, an Italian algebraist had Cosa, and by the 16th century, various people were using an abbreviation for it. Everyone had a symbol for what they were solving for. What nobody had was a symbol for the numbers given in the problem, which meant that every problem was a specific problem. You could not write down a general quadratic, you could only write down this quadratic, with these particular numbers in it, and then demonstrate a method by carrying it out. That is why Al-Khwarizmi's canonical example is a square and 10 roots equal 39, a real number of roots, a real number of dirhams, and why he had to work each of his 6 cases through on a specific instance. The method was communicated by example, the way a cook teaches by cooking. Viète's move was to let the coefficients be letters too. He used vowels for the unknown quantities and consonants for the known ones. And with that single convention, a mathematician could, for the first time, write down a statement about every problem of a given shape at once, and prove it once, for all of them, forever. He gave the 2 activities different names. Calculating with numbers, he called the numerical art. Calculating with these general symbols, he called the art of species, kinds of types, the general form rather than the instance. That is the difference between a recipe and a law. A recipe says, for these numbers, do these things. A law says, for any numbers whatsoever standing in this relationship, this must follow. Mathematics had been proving general statements since Euclid, but it had been proving them about geometry, about all triangles, all circles. Viète handed algebra the same power, and in doing so, he made it possible for a formula to be a theorem. He was not all the way there, and the ways in which he fell short are interesting. His notation is still verbose, half Latin, and half symbol. Where we write a compact line, he writes something closer to a phrase. He accepted only positive quantities. And he was still bound by a rule inherited from the Greeks that would strike you as bizarre. The rule is homogeneity, and it goes back to the wreckage of chapter 3. When the diagonal of the square broke Greek arithmetic, the Greeks made geometry their foundation, and in geometry every quantity is a kind of thing, a length, or an area, or a volume. You can add a length to a length. You cannot add a length to an area any more than you can add 3 miles to 5 gallons. It is not that the arithmetic is hard. The statement is meaningless. So when a Greek or Viète saw the unknown multiplied by itself, that was an area, and the unknown multiplied by itself twice was a volume, and you could not add the two together. Which means the perfectly ordinary modern expression that adds a cube of the unknown to a plain multiple of the unknown was, in 1591, not merely ugly but ungrammatical. Viète worked around it by attaching dimension labels to his coefficients, insisting that this constant is a plane and that one is solid, so that everything in a sum came out the same dimensional kind. He was carrying, in other words, a piece of luggage the Greeks had packed 2,000 years earlier, and he could not put it down. Somebody was going to have to explain why algebra did not need it. And the man who did also demolished the wall between algebra and geometry entirely. Before we get to him, a short detour, because there is a lesson in it we met in Chapter 10, and we'll meet again. In England, at almost exactly the same time, a man named Thomas Harriot was doing algebra, at least as good as Viète's, and in some respects better. He had a cleaner notation. He was comfortable with negative, and, in some contexts, imaginary roots. He introduced the greater than and less than signs. He also turned a telescope on the moon several months before Galileo did and drew what he saw, observed sunspots, and worked out the law of refraction in optics before anyone published it. He was a considerable man in his own world, Walter Raleigh's household mathematician, sent to the Virginia colony as surveyor and scientist, author of an intelligent report on the place and its inhabitants. He published almost nothing. His algebra came out 10 years after his death, edited by other hands into something noticeably worse than what he had written. His optics stayed in his papers. His astronomical drawings sat unremarked for centuries. The result is that Harriot is a name in specialist histories, and Viète is in this chapter, and the difference is not talent. Discovery is not enough. A result that does not enter the conversation does not do anything, however correct it is, which is the same point Madhava's Infinite series made in Chapter 10, from the other side of the world. Now to Descartes, and I want to start with the night that made him. He was born in 1596 in Touraine, educated by Jesuits at one of the best schools in Europe, and took a law degree he never used. Then, in his early 20s, he did what a certain kind of restless young gentleman did. He joined an army. Not to fight, particularly as a volunteer, with means seeing the world at someone else's expense. In November 1619, he was in winter quarters in southern Germany, in a room with a stove. On the night of the 10th, he had 3 vivid dreams, one after another, and woke convinced that he had been shown something. That all of human knowledge could be unified, that the key to it was the method of the mathematicians, and that it was his job to do it. We know about this because he wrote it down in a notebook, and although the notebook is lost, an early biographer had seen it and reported the contents. So the dreams are as well attested as anything in a private life gets. Take them how you like, as a vision, as the ordinary strangeness of sleep, as a young man's ambition arriving in fancy dress. What is not in question is that he spent the rest of his life executing on it. You will sometimes read that he conceived the idea of coordinates while lying in bed, watching a fly crawl across the ceiling, realizing that he could specify the fly's position by its distance from 2 walls. It is a wonderful image. It appears nowhere in his writings, surfaces long afterward, and belongs on the shelf with the naked run through Syracuse and the golden thigh of Pythagoras. Good stories about great men are among the most durable things in the world, and among the least reliable. In 1628 he moved to the Dutch Republic and stayed for 2 decades, changing address constantly, well over a dozen times, in pursuit of quiet and of a country where a man could print what he thought. He needed both. In 1633, he had a book of physics finished and ready, and then news arrived that Galileo had been condemned in Rome for saying the earth moves. Descartes' book said the same. He put it in a drawer and left it there. That decision is worth sitting with. The most influential philosopher of the century looked at what had just happened to the most famous scientist in Europe and quietly suppressed his own work. Then he spent 4 years figuring out how to say most of it anyway, wrapped in something harder to prosecute. What came out in 1637 was the Discourse on the Method. He published it anonymously. He published it in French rather than Latin, a deliberate choice aimed at readers outside the universities, including, as he said, women who were not taught Latin. And he published it with 3 appendices, whose purpose was to demonstrate that the method actually produced results. The first was on optics and contains the law governing how light bends when it passes from air into water. The second was on weather and contains the first correct explanation of the rainbow, worked out in part by filling a glass sphere with water and tracing what the light did. The third was called La Géométrie, and it is the reason he is in this book. Here is the idea, and it is so familiar that the effort is in seeing it as an idea at all. Draw 2 lines at right angles. Now, any point on the page can be specified by 2 numbers, how far across and how far up. Nothing else is needed. A point, which had been an undefined primitive since Euclid, that which has no part, has become a pair of numbers. And now the consequence, which is the whole chapter. Consider a circle of radius 5, centered where the 2 lines cross. What is a circle? It is the set of all points exactly 5 units from the center. Now take any point on it, at some distance across and some distance up, and drop a right triangle. The horizontal distance, the vertical distance, and the radius as the long side. That is the Pythagorean theorem, and it has been waiting for this moment since chapter 3. The square of the horizontal distance plus the square of the vertical distance equals the square of the radius. 25. So the circle, the shape, the drawn curve, the object of pure geometry, is precisely and exactly the set of number pairs satisfying one short equation. Not corresponds to. Not can be modeled by. Is. The curve and the equation are the same object described in 2 languages. And once you see it for the circle, you see it everywhere. A straight line is an equation. A parabola is an equation. The ellipse that Kepler had just discovered the planets travel on as an equation. Every curve the Greeks had studied by construction, and a limitless supply of curves they had never imagined, is an equation. And conversely, every equation you can write down describes a curve, whether or not anyone has ever drawn it. Geometry and algebra had been separate provinces since the diagonal of the square drove the Greeks apart from number 2,000 years earlier. Descartes showed there were one country with 2 languages and provided the dictionary. Now watch what a dictionary is worth. Ask a Greek geometer whether a particular straight line crosses a particular circle, and he must construct the figure and reason about it. And if the answer is subtle, he must be ingenious. Ingenuity does not come on demand. Ask the same question with coordinates, and it becomes, does this pair of equations have a common solution? That is an algebra problem. You substitute one into the other, you get a quadratic, and the quadratic solutions tell you the answer without your having to be clever at all. 2 solutions and the line cuts through, 1 and it grazes, none and it misses entirely. Turn the crank. That is the superpower. A hard problem in one language may be an easy problem in the other, and now you can move between them at will. Geometry gets the mechanical, grinding reliability of algebra. You no longer need a flash of insight. You need to do the algebra correctly. An algebra gets the eye. An equation, which is a line of symbols with no intuitive content whatsoever, becomes a shape you can look at, and looking at it tells you things. Where it rises, where it turns, where it crosses 0, how it behaves far out. Every graph you have ever seen descends from this. Every chart in a newspaper, every plot in a scientific paper, every line on a screen tracking a stock or fever or a planet's position is Descartes' dictionary being used in one direction. Turning numbers into a picture so that a human eye, which is extraordinarily good at shapes and hopeless at columns of figures, can do the work. 2 honest deflations, because the popular version of this story overstates it in a specific way. First, Descartes did not draw the thing you are picturing. There is no grid in La Géométrie. There is no vertical axis in our sense, no 4 quadrants, no systematic use of negative coordinates, and almost nothing that looks like plotting an equation to see what shape comes out. He generally works with a single reference line and constructs the second direction as he needs it, often at an oblique angle rather than a right one. His usual procedure runs from the curve to the equation, not from the equation to the curve. The apparatus we call Cartesian coordinates, perpendicular axes, negative numbers running both ways, the whole plane covered, was assembled over the following century by the people who read him, annotated him, translated him into Latin so the rest of Europe could follow, and gradually straightened the thing out. The name is a tribute, not a description. Second, he did not do it alone or first. Pierre de Fermat, whom we will meet properly in the next chapter, had worked out his own version of coordinate geometry by about 1636, before the Géométrie appeared, and circulated it in manuscript among his correspondents. In one respect, Fermat's version is closer to how we do it now. He starts from an equation and asks what curve it describes, which is the modern instinct. He did not publish it. He did not publish much of anything. He was a provincial magistrate who did mathematics for his own pleasure and told his friends about it in letters. His treatise came out after his death. The two men then quarreled about it, and about optics, and about tangents, with the sharpness of two proud people who each know they got there on their own. Neither was lying. It is the same phenomenon we watched in Chapter 10. When the conditions are right, a discovery becomes available, and more than one person picks it up. There is one more thing in La Géométrie that looks technical and is not. Descartes killed the homogeneity rule. Remember Viète's problem. A length times a length is an area times a length is a volume, and you cannot add things of different dimensions. Descartes noticed that this whole edifice depends on a hidden assumption, that a product must be interpreted as a region. So he reinterpreted it. Fix a segment and call it the unit. Then, given two lengths, you can construct a third length that stands in the same relation to one of them as the other does to the unit. A straightforward business with similar triangles. Call that the product. It is a length. Two lengths multiplied give a length, and you can multiply as many as you please and never leave the world of lengths. With that one construction, the dimensional straitjacket falls off. You may now add a cube to a length and a length to a number and write any polynomial you like without apologizing. Algebra is released from having to mean anything geometrically, which is precisely what allows it to describe everything geometrically. And now watch the door this opens, because it is a very large door. A point on a line is one number. A point on a plane is 2. A point in space is 3. Ask a Greek what a point in 4 dimensions is, and the question is not hard, it is nonsense, there is no fourth direction to point in, there is no such space, the words do not refer. Ask it with coordinates and the answer is 4 numbers. That is all. And every piece of machinery you built for 2 and 3 numbers keeps working. You can define the distance between 2 of these points. The formula is just the Pythagorean pattern with another term added. You can define a sphere. All points at a fixed distance from a center. You can ask whether 2 such spheres intersect and answer it by algebra and be right. You cannot see it. You will never see it. But you can calculate in it with total confidence, because the geometry has been fully translated into arithmetic, and the arithmetic does not know how many dimensions it is supposed to have. This is not a curiosity. It is how essentially all modern quantitative work is done. A physical system with 1,000 moving parts is a point in a space of thousands of dimensions, and its evolution is a curve through that space. An economy, a climate model, a protein shape are all handled this way. When a machine learning system processes an image, it is treating that image as a single point in a space with as many dimensions as the image has pixels, and finding surfaces that separate one region of that space from another. Geometry, done at scales no eye could follow, entirely by arithmetic, in a space no one can picture. Descartes made geometry independent of what human beings can visualize. That may be the single most consequential thing in this chapter. A word about the philosophy, since the geometry was an appendix to it. The Discourse is where Descartes lays out his method for reaching certainty. Doubt everything that can possibly be doubted. Keep doubting until you reach something that cannot be doubted at all, and then rebuild from there. The famous conclusion is that the one thing he cannot doubt is that he is doubting, that there is a thinker doing the thinking. I think, therefore I am. Everything else has to be reconstructed on top of that single fixed point. You have seen this shape before in Chapter 4. Strip your reasoning back until you reach assumptions that cannot be argued further. Declare them openly. Build everything else on them, admitting nothing that has not been earned. That is Euclid's machine, pointed at philosophy instead of triangles. And Descartes was entirely explicit that the geometers were his model, that theirs was the only body of human knowledge that had ever achieved genuine certainty, and that the trick was to work out what they were doing and do it everywhere else. Whether it succeeded is another matter. His physics, in which the universe is filled with swirling vortices of matter, was wrong and was demolished within a century by Newton. His account of the relationship between mind and body has been a problem for philosophy ever since, rather than a solution to one. The dream of deriving all knowledge from indubitable first principles has not gone well. That is roughly the story of chapters 21 and 22, where the same dream is dreamed again. More rigorously by better logicians and destroyed by a 25-year-old in Vienna. But the Géométrie worked. And within 30 years of its publication, 2 men in England and Germany would use coordinates and equations to do something nobody had managed since Archimedes: to compute exactly what a curve is doing at a single instant. Descartes died badly. In 1649, Queen Christina of Sweden, 19 years old, brilliant, and determined to collect the greatest minds in Europe, summoned him to Stockholm to tutor her in philosophy. She wanted her lessons at 5 in the morning in an unheated library in a Swedish winter. Descartes had been a late riser all his life and had told people that the best of his thinking was done in bed. He caught pneumonia and died in February 1650, age 53. Next, the letters. In 1654, a French gambler with a problem approached a young mathematician in Paris. The problem was this: if 2 men are playing a game of chance for a stake, and the game has to be abandoned partway through, how should the money be divided? It sounds trivial. It had defeated everyone who had tried it for 200 years, including Pacioli and Cardano. And the correspondence it set off between 2 Frenchmen who never met would do something more radical than anything else in this part of the book. It would make the future calculable.